Hi, welcome back. So in the last tutorial we drew the 3D transformer, and now we're going to analyze it for some parasitic extraction. And the reason that I think this is interesting is because I want to be able to make some more accurate SPICE models and do some other analysis. And for that I need to know the parasitics of the transformer. And so this is a way that might be good to do this without having to buy the actual parts and build the transformer. So we'll see how it goes. So we finished making this geometry in the last tutorial, and now we're going to simulate it. So let's see, what do we want to simulate is the first question. Here's a article I'll put in the description from Ridley Engineering, and he's talking about measuring transformers. So this is something you might measure in the lab to make a model for maybe a circuit simulation. Here's the simplified model here. You have the magnetizing inductance. This resistance is representing the core loss. And then we have leakage inductances. You can have a leakage on the primary. You can also measure leakage on the secondary. And then you have the coil resistance and the primary self-capacitance and secondary self-capacitance. Then you have the mutual capacitance between the two windings. Now if you have multiple windings on this side, then you end up with kind of the same thing, just this copied down, except that you have a mutual capacitance for all combinations. So from here to here, from here to the other one, and between these two. So the core loss is kind of tricky. We're not going to simulate this RC here, but we're going to simulate the rest of these variables and create this simplified core model that we can then use in a SPICE simulation. So there's a couple other articles by COMSOL which are pretty handy that go over some of this stuff. I'll put links in the description. Nice thing about those is at the bottom they have a spot where you can download the model. So following the workflow, we're going across the top here. Did the geometry, next is the materials. So we're going to add materials, and let's see, try that again. So here's the materials. We want a core material, a wire material, and this air box material. So we look in the built-in materials. We have air, double click on that, and it takes a second, but it'll show up over here. There we go, we can minimize some of these guys. Now that we have the air, we can add some copper for the wire. So now we're going to come down here. We want nonlinear magnetics and iron powder. They have alloy powder. So this one is a MPP 200. Double click that. So you have to be a little careful with these. Some of them you have to enter the permeability. I don't see a spot for entering this one, but some of them start out as 0 and you have to put in the 200. So we can go to the air here. The air selected everything. So we want to click here to clear the selection, and we only want this air cube on the air. So for the copper, we're going to have to hide this. We can go here to the hide and click on here, or I have this, I can just enable this. It's already there to hide it. So for the copper, we're going to select, let's see, this hiding thing is always tricky. We'll just reset the hiding, and we want to hide this. All right. So the copper, we're over here. We want to escape to get out of this hiding mode. And the copper, we're on domain selections. So I want to change this. Let's see. So it's only letting me select the domains right now, not the whole object, which is kind of annoying. So for this one, I'm going to do the selection box up here. I'll just select everything, and I want both windings to be copper, so this shouldn't be a problem. I just need to deselect now, just one click to deselect the core. So now I just have all the wires selected. Now for this powder core, I need to select the core. And we have everything selected here. And in the very first video with the intro, I mentioned this. The air gives convergence problems with zero conductivity. So I'm going to go down here and look for the electrical conductivity. I'm just going to make that 1 for now. So that's it for the materials. The next is the mesh. So we can click up here. Oh no, sorry, it's physics. Go across the top. So physics. I want to add physics. We already have the tab open over here. Let's add physics. And the first type of physics we're going to want to do is we want to do the open and short circuit tests. So when you connect up here and to the primary a signal, you measure the inductance with the secondary open and shorted. So when you connect the signal up here and you have this side open, then this side is not really doing a whole lot. So you're measuring this LM right here. And then when you short this side, that's kind of canceling out this LM. So then when you measure here, you're measuring this leakage. So we want to set up an open and a short magnetics test. So we can go over here with the AC/DC electromagnetic fields, and we want this magnetic fields MF. We're going to need a few of those, so I'll just double click on one to start. So here we have magnetic fields. We can give it a name too. So I'm going to call it short circuit primary. So now we want to right click on here. We're going to add a coil and do that twice. We have 2 coils. So we'll make this the primary and call this one the secondary. Now we have to assign these guys, but if you'll notice this little X came up here, and oh, this is what I was talking about. So I guess it doesn't show the permeability and the conductivity until you add one of these studies. So you got to fill that in now. So permeability we know is 200, and the conductivity just have to look up. That is 5.998 e to the 7th Siemens per meter. So now you can see it's okay now. If we go back to here, we can select these domains. So it's kind of slow selecting all these separate domains. And there's a couple of things that I noticed. Also noticed there's this little extra point down here I forgot to remove from the geometry. So I actually want to go back to the geometry and make a couple changes to that. So we're going to go here to the sweep, and there's this checkbox here, create cross-sectional faces. So if we uncheck that and we build that again, you can see it removed all of the intermediate faces. So this is kind of just like a single domain now, this wire. It's just like one smooth wire. And then you can, they have these shortcuts here, F7, where you can right click up here and do build preceding. It'll build the rest of this. So now we have 2 separate wires here. So to remove the points, I'm just going to do a delete entities and change the selection to point. Get that point. If you hold down the left click, if you hold down the right click and drag, then it pans like this. So we got those 2 points, build selected, and they're gone. The other thing I'll just point out real quick is if you want to remove stuff for the simulation, you can go back here and change your build order, but that's more complicated than just making another delete entities thing. And you can do something here, like if I go delete, I can say I just wanted one coil, then I can do objects here or even domains now. To click this, build selected. Wow, okay, I think I just got another error. So when I deleted that one, it doesn't look like it got deleted, and that's because it looks like there was one on top of the other one. So let's see if we undo this. Well, let's see, let's just add another one. We'll do another delete and do domains. So if we delete this one, now it's gone. Control Z, we can undo. We can delete this one. Now they're both gone. Okay, so there's got to be something wrong with this rotate here where we copied the primary, made the secondary winding. And on this angle, oh man, it looks like there's a little typo here. There's a little 0 at the beginning. So if you click in here and then over here, it leaves the original 0 and then puts the range in. So I think that's the problem. So let's see, build selected. Now we can, each one of these we can build with F7 as a shortcut. This is deleting these 2 points. All right, so F7, we delete the 2 points. And this one here is, we'll just get rid of that. This is the one here, build selected. Oh, now it's gone. Okay. So that works. So now we've got everything set up the way it should be. We can get rid of these, either disable them or delete them. I'll just delete them. But you get the idea. So now, like here, you could delete that. And then if you want, you can just right click on here. And you can't really see it because it's off the screen. Let's see. You can do disable. Now that's disabled. So if you go to this guy and build preceding, back to having the 2, and F7 build this, and now we're back to having the error cube and everything. So let's go back here to our coil primary, and hopefully it'll be easier now. We can select, we'll just say this first one's the primary. Now we have the primary coil selected. For materials, I like to always do from materials, material type. And we have a coil name, I'm going to call this primary. So it's a single conductor, because we modeled the whole conductor. And this one, we're going to inject a voltage on it. I'm just going to say like 10 volts, but it's kind of nice to do these with parameters. Let's go up to the top here. We'll add a new parameter. We'll just call this V primary. 10. We can do volts with the brackets. We can do one for the secondary too, just in case. We'll make it 10 too. Then we come back to here. Now we can just do V here. So we have the voltage set up, and the rest of the stuff is pretty much just leave it. We got secondary here, we'll do the same thing, so we can select the secondary. So the test we're doing right now is the short circuit test. So we want this secondary here to have a short, which is essentially 0 voltage. So we're going to put this on voltage, and we'll put 0. So that's simulating a short circuit. We'll call it secondary. So now we have the primary and the secondary coils set up, and we just need to define their inputs. So that's going to be a face that defines where the current is starting. So for this one, we want to get this face right here at the top. We'll just say starts at the top, flows around, comes out the bottom. And for this one, do this one over here. So we've got the primary and secondary input set up. So that's everything. And we could do, for the core and the air, you could do like an Ampere's law, but they're already covered by this Ampere's law that goes over the whole system. So we don't really need to add another one. So we can go here, this little MF, that's going to be referenced in the results. So I like to change that something like short circuit primary, SCP. And now we're going to make one for the secondary. To do that, you can right click, and sometimes it'll say duplicate in here. It's kind of off the page. Let's see. I don't know if I can get it to where you can see it, but if you right click here, you go down and it says copy. So you can click copy, and then you can right click up here and it'll say paste magnetic fields. So that way you can duplicate it. Some of them, when you right click, it says duplicate, and some of them, let's see, so we can just say okay on this. Some of them you have to copy and paste. So this one here we're going to change to, oh, the typo on that, short. Change this to secondary. And we'll do SCS for secondary. Now we want to change in here is just the primary is going to be 0 volts, so that'll be shorted, and the secondary we'll put V sec. And that's it. So now we have a short circuit primary and secondary test. So now it's time to do the open circuit, and we can still just paste the same one here. So if we right click, paste magnetic fields, this one we're going to call the open circuit primary. So open circuit just means no current is flowing. So we can just go in here. And the other thing is when you copy and paste them, see I named it primary and secondary. When you paste it, it gets rid of all of those coil names for some reason. So you got to go back and rename them. There. This is just convenient for when you're looking through the results to see what it is. All right, so in this we have the V pri still. And so for the open here, instead of 0 voltage, we just want 0 current. So that's open circuit. Now we can copy this one again. Change this one to secondary. Copy these coil names again. And just swap these. So this will be 0 current, and this one will be V sec. Now it looks like, so this one is SCP, SCS. Name this one OCP and OCS. So next we want to do the intrawinding or self-capacitance. So that's going to be over here for the AC/DC, electric fields. I want to do one of these electrostatic physics. So we can clean some of these up a little bit, make it easier to see. So we want to add a couple of terminals on here. And for this one, we're going to use this object terminal up here, not this terminal down here. So I guess that's the, well, it's the domain, I guess, not the object. So it's the domain terminal, and the other one is the boundary terminal. So we want the domain terminal. We need 2 of those. And then I think it helps the convergence and makes it a little more legit. I'm not sure if it's 100% necessary, but we want to do a floating potential on the boundary down here. And also a ground on the boundary. So we're going to use the air cube is going to go to the ground, and then the core will go to this floating potential. So first we can rename this. We'll put self capacitance primary. We'll call it SC. That's short circuit, so we'll just do SP for primary. And let's see, going down the list here, this has everything. So terminal 1 we'll call primary, and we're going to select this one. Let's see, terminal name, primary, and we're going to do a voltage. So for this one, we're going to put the primary voltage on the primary coil, and then we're just going to short the one that we're not using. We're just measuring the the capacitance on the primary. So secondary here, we're going to select the secondary, and the floating potential is the core. So we want to select the whole core. These guys are going to get in the way a little bit. We can just can select this selection box. Select everything. I guess we already did select everything. Let's try that again just to be sure. So we're going to select everything, and then, oops, if you hold Control and you try and rotate it, it gets a little weird there. So we're going to deselect this one. Deselect, let's see, so we can only do boundaries right now. So it looks like this is a little tricky. So I think what I want to do is try and hide some more stuff in this hide for physics. We can do this transparency up here. That'll let us see inside of stuff. So if you do the scroll wheel, see this, I'm just doing the scroll wheel on the mouse. It'll let you kind of get inside stuff and select what's underneath it. So it's kind of scrolling through the selected items. So what I want to do in here is just scroll through. I'm going to hide that one. Scroll through, I'm going to hide that one. So now these should all be hidden. If I go back, floating potential, now see we just have the cube. So we'll do selection box. Okay, first we'll hit this little brush, clear the selection box, select all of this. Now that we have it, just for future reference, you can click on this create selection, and we're going to call this core, and those are that boundaries. I think it's boundaries. Yeah, we're in boundary mode. Okay, so now I want to go back, and this will be in this drop down. You can see that it's also up in the selections now. We have core boundaries. Go back to the hide from physics. We can get rid of all of this stuff really. But what we actually want now is just to unhide this box. So we can go back to the ground here. Now we can select this box. This one we can just do each face because there's not that many faces. There we go. So now we have all the faces selected, and we'll save that as a airbox boundaries for the future. Okay. So this one's the air box. Now we can go back. This whole hide thing it seems to me like it could be done a little bit easier to be able to select stuff better. But we'll get rid of this, and let's see. Just do the air box for right now. And we're back. So I need to copy this one. We'll do right click, copy, right click, paste electrostatics. The secondary, call this SS. So for this one, I'm just going to change this to 0. And we'll name this terminal again. Copy it from here. This one's going to be secondary voltage. These guys will be the same here. So that's it for the two capacitance, the self-capacitance for the primary and the secondary. Now we just want to do the mutual capacitance or interwinding capacitance between the primary and secondary. So for that one, we're just going to copy and paste this again. This one's mutual capacitance. And this one we can just use 1 for the mutual capacitance. Let's see, mutual. We'll just call this. So now we have all of these again, and it's going to be pretty much the same, except we're just going to change this to 0 charge. And go ahead and do these. Rename these primary and secondary. So that's the mutual capacitance. So the last one we want is going to be electric currents. So we get in here electric currents EC, and that'll be for the DC resistance. So for this one, we're not really too worried about the core of the air. We're going to do terminals. For this one, the terminal is actually going to be one of these boundaries, because the terminal in this case is where the current starts flowing into the object. So we'll do 2 of these, and we also need a ground. And the first terminal here, how it's going to work is it'll go in here, and the ground will be these 2 bottom points. We can name these primary and secondary. And in this case, we want some current, but we're just going to put 1 amp for each one. We can do the terminal names too, I guess. It doesn't really matter what these currents are, because we're going to be dividing it out to get the resistance. We can put a title up here though. Resistance. So that should be good for the physics. Now if we look up here, the next one is the mesh. Mesh is pretty simple in COMSOL. Well, it has a lot of options, but you pretty much just can do this level of fineness. It'll automatically set it up, and you can just do build mesh. So here it is on the normal setting. You can see it's pretty all right. It probably worked just fine. These wires are kind of like, they're not exactly squares, but they're kind of square. So I think, well, no, they've got, maybe they're octagons. Anyway, I think for this, I'm just going to do fine and try that. Okay, so there you can see what fine does. So fine will make the simulation take longer, but it will help. It will make more accurate results, and will also help with convergence. So I think I'm just going to do that for this one. So after that, we go to the next one, which is study. So this is basically simulation settings. I'm going to add a study. brings up this over here. And I'm going to do one study for each of these physics and just link it each one to one. So these first ones here are going to use frequency domain. I'll double click on that. And because we're studying these coils, we also need to do this other one here, this coil geometry analysis. So it gave us an extra study, but you can just drag this up here inside of this study. The coil geometry one doesn't take very long, so you can just do it for each of the studies. I'll right click on this one, or you can just hit the delete key. Get rid of that extra study, the empty study. And now for the coil geometry, well, let's give it a name first. So this one's going to be, now we can just copy this up here. Short circuit primary. And in here, we just want to select only the short circuit primary. And this one is frequency one here, same thing. Deselect all these physics here, so we just have the top one. And this is where we decide what we want to do for frequencies. So I'm going to change this to kilohertz. And let's just say this is a switching converter that's running at 300 kilohertz. So maybe we put in here 300, but we want to do a couple different, we can try 1 kilohertz, maybe 10 kilohertz, and 300. So we got 3 different frequency sweeps we're going to measure at there. And that's it for setting this up. So actually, when you right click on here, there's no duplicate or copy. There's this copy code, but that's not what we want. So to make more of these, actually I could have just left that empty study. So you can make an empty study and then copy these, paste them in here. So it has a paste multiple items. When you right click here, this paste multiple items. So we can do that. Let's see, we only need 2 right now. So just set this up the same as the other one, except now we're going to select this second one. We'll just do a couple more. So for the self-capacitance, we're going to do this stationary one here. Can do a couple of those. And for the mutual capacitance, we're going to do, let's see, there's this suggested here, stationary source sweep. It's this special one here. And for the DC resistance, we'll do another stationary. So you don't have to do this the way I did with the one study for each physics. You could kind of stack them together and maybe it'd be a little simpler that way, but I kind of like this because then you can make sure you're just running one at a time, whichever one you want. So here we'll copy and paste these names. Now I just have to uncheck all of these except the one that we're doing here. So the last thing I like to do, now that we've made so many of these, is to do one more empty study. And we'll put that one up at the top here. And this I'll just call multi-run. And then you can right click on that and you can do study reference. So how many do we have here? We've got 1, 2, 3, 4, 5, 6, 7, 8. So now we can reference each one to one of these. So now we're going to start off running these one at a time, but if you get a few going, then you can just run this multi-run and you can run them all at once, or if you want to just run like the first 4, you can do Shift to select these, right click, and disable. Now if you run this, right click, you can do compute, it'll just run these 4. So we'll just start with the short circuit primary, and now we're all ready to run the simulation. So up here you can do compute, or you can right click and right here. While that's running, there's a progress tab here. There's also this progress bar here. You can click this to cancel it. If you have it set up, sometimes a tab will pop up here that'll show you kind of if it's converging or not. After it's done running, when you press this arrow down, it'll have extra simulation settings in there. Alright, so this first one finished in 18 minutes and 42 seconds. You can see the convergence plot here. So it didn't have too much trouble converging. So I'm just going to go for it here with the multi-run. So I'll get the rest of these enabled, and I'll just disable this first one since we already ran it. So disable, and go ahead and save this, and then we'll run the multi-run. Alright, so it looks like it did make it through all these electromagnetic simulations, and it got stuck on the first, well, looks like it made it through a couple of the electrostatics, and it got stuck on the mutual capacitance. It says, this is the one that's the special sweep, the stationary source sweep. It says in this error that the name is primary, but it needs these to be integers. So I think changing the coil name to primary for that didn't work, and I need to just change it back to 1 and 2 for primary and secondary. Let's see. And we'll just make this a 1, this a 2 for the terminal names. And we can save that. And we'll just run this one by itself here. So that was the mutual capacitance. Okay, so it looks like the mutual capacitance simulation finished in 5 minutes, and the resistance one I ran after that, it took 4 minutes 23 seconds. So we're all done now and ready to post-process the results. So I'm going to make some of these evaluation groups. We'll make one for each of these sections here. So we'll make 4 of those. And this first one we'll call open circuit. So it'll be short circuit, self-capacitance, and last one will be DC resistance. I guess maybe to make that clearer, we can call this one magnetizing. And we can call this one leakage. Okay, we want to add some of these global evaluations. So we'll add one for the primary, one for the secondary. So these, you can say which data set they're coming from. If we had more of these in, like if we'd had just one of these short circuits studies covering both of these physics, then we could just have one of these reference that data set. But since we have a couple of data sets now, then we'll just have 2 of these evaluation groups. And so this one is going to do the short circuit primary, and this one will be the secondary. Having the primary and the secondary for this magnetizing inductance isn't really that important because we only care about the magnetizing from the primary, but we'll just do them both for kicks. So primary and secondary. All right, so if we want to calculate the inductance with impedance, we would say Z equals J omega L, right? So we want to solve for L. So we're pretty much just putting the J omega under the Z, and we're saying that Z is the voltage divided by the current. So L is going to be equal to voltage divided by the current, and we're going to divide that by J omega L, or no, J omega, but J omega is 2 pi times the frequency. So that's how we get this formula. So we have voltage of the primary, and then the current of the primary, we need to figure out what that is. So this is SCP test here. We can just do control space, and that'll show us what's available because we already have this primary short circuit selected. So we want short circuit, primary, coil parameters. So we can just do SCP.I, that limits it here. And we want primary coil current. So there's that. And this is primary magnetizing inductance. Okay, so I forgot to put the imaginary part on here. It's giving me complex numbers, so we just want the imaginary part of this. And I'm going to duplicate this one. Let's rename this one secondary. We'll change this to secondary high coil secondary. Secondary here. All right, now let's move it down to this one. So it's giving me the primary here and not the secondary. I'm just noticing here we've got magnetic flux density here. We've got the SCP, and then it goes to the MC. So that's here going to here. So it looks to me like I thought I ran this multi-run, but I guess it had an error, and so maybe it didn't save any of the simulations. Let's see in the log here. Got the short circuit primary. We've got the mutual. Yeah, so it's almost like, I guess when it failed the multi-run, it didn't finish any of the simulations. I had thought that it went through the first ones and it just stopped here. But I gotta rerun these. Maybe I'll just do them one at a time. I gotta rerun all of these simulations here. So I reran this, and it didn't actually show up in this list here. So I'm not sure exactly what's going on, but I noticed that I can't do the secondary values for this primary one either, the first run. So when I just try and do this, it gives me this error about the secondary. So I'm just kind of wondering if it doesn't like the name of the secondary. So I'm going to rerun this last simulation again, this short circuit secondary, and I've renamed these guys just pri and sec to make the coil names shorter and see if that makes a difference. So shortening the coil names didn't make any difference, and I think I noticed what I did here. So if you look at the difference between primary and the secondary on all of these, is I forgot to set the material. So here it says from material, and this one it says non-solid. So I need to change all of these secondaries since I copied and pasted everything. I need to change the material type to from material. And I tried rerunning that for this first one up here, and now it works. So I'm going to change all of those and rerun these guys. Okay, so I reran these open and short circuit magnetics ones and then the self-capacitance ones as well, and you can see they show up down here now, so everything's finished running. And I noticed I was getting confused up here too, I think, because I called this open circuit, but I selected short circuit. So I'm going to switch that here. So this is open circuit. And this one, we want open circuit. I think I put the open circuit on the top here and the short circuit on the top up here. So I think that's what I was getting confused about. So now this one is going to be the magnetizing inductance. And we have that up here. And this one here we can duplicate. Call this secondary. And that should be the same. So we have the primary here, open circuit. And this one we'll do open circuit secondary. And we'll call this secondary magnetizing inductance. And then this right here, we need to change V secondary. I mean, I made the primary and the secondary the same, so I guess it's not going to make much difference in this particular case, but we could change the variables and rerun it. Let's see. So this is SCS coil secondary. Now if we evaluate this, yep, we got zeros. Yeah, so I'm still confused here. It looks like this is open circuit here, not, so it should be OCP. And same with this one. All right, let's try that. So that calculated, or what do we have here? It looks like we're getting different values for primary and secondary, so that doesn't make sense right off the bat. What should it be? So if we look at the data sheet for the core here, it says AL is 90 nanohenries per turn squared. So if we have 10 turns, that's 9 microhenries. So none of these are very close. This is 0.9 microhenries here, but we don't have 9 microhenries. This is 3. So we'll have to see what else we can find here. Another thing I wanted to check here is if I change this to none, because this is technically not flowing down, then these here are each referencing their respective data sets. There's also this multi-run one here, so I want to see if that changes it. So we'll see if this is 9e to the negative 7th. Okay, so it fails with the multi-run. So we'll just keep this on open circuit 6. Well, I'm just going to finish filling out these different formulas here before I try and troubleshoot what's going on with the inductance. So the next one here is the leakage inductance. If you're doing these here not all linked with from parent, then might as well make the parent just none. So I'm going to make this one here is the short circuit primary. So we have that. And it's the same formula here for the inductance. It's just different now because it's the short circuit test. So we can duplicate this one. We can call this primary. Duplicate. Secondary. So we need to change this. Short circuit. Secondary. And this is S. Can calculate that. Okay, so the leakages are at least about the same. So that makes sense. And so the self-capacitance, if we look in, we'll add a couple of these global eval groups. Let's see. Set this one to none. This one we're going to do self-capacitance primary. And if we look in here, just control space, we can see what's available. They've got these energies and powers. So the total electric energy, and we know that the energy of a capacitor is 1/2 CV squared. So we can use this to calculate the capacitance. So if you have 1/2 CV squared, then we need to move the half to the other side. So that's 2 times the energy. And then we divide that by V pi squared. And that should be, yep, capacitance here. So we can call this primary self-capacitance. And we calculate that. So that's 4.6 e to the negative 12. So that's pico. So we can change this up here to pico and recalculate it. And now it'll show it as 4.6 picofarads. This one we want to be primary. Duplicate that one. This will be secondary. And they're about the same, so that's good. Next we have the DC resistance right here. So we're skipping the mutual capacitance right now. I'll show you that's in a different form here. So for the DC resistance, we're just going to do V equals IR. So we'll do a couple of these evaluations. Let's see, primary. We can actually write both of these in this one, since it's all from the same simulation. So we're going to do V equals IR. So R is V divided by I. We want the resistance. So there we have 10 ohms of resistance. So that's definitely too much resistance, so we'll see. Maybe that'll give us a clue to our issue here. If we just want to check out the current, saying we're getting 1 amp of current. Let's see. Okay, yeah, so I calculated that wrong. We set it to 1 amp. So we don't actually want to put V primary. We want to put the calculated value. So it's EC dot V. So we want the primary voltage. Okay, that's a little better. So now we have 20 milliohms. We can change these to milli. There we go. So 20.9 milliohms. So that's pretty reasonable. So now for the mutual capacitance between the different windings, we did this stationary sweep, and that created this lumped thing here. And this actually has a few different matrices that it calculates for you. So it's got the inverse Maxwell, the regular Maxwell, it transforms from that, and then the mutual capacitance, which is what we're after. And there's this article here I'll put in the description from COMSOL on their blog, how to calculate a capacitance matrix. And what it's showing here is this Maxwell to mutual. It does this transform, but it basically puts it in this form. So you have mutual from primary to primary, primary to secondary, secondary to primary, and secondary to secondary. The ones that we're after are these two are the same. It's between the primary and the secondary. So if you look at our matrix down here, this is the mutual capacitance right here. So 3.9, which is the same as this one. So it's 3.96 picofarads. And I haven't found an easy way to label that. but that's the one it is right there. So you just have to click in here, mutual capacitance. If you have multiple windings, it'll be the ones that are up from the diagonal ones. Okay, I'm looking through these physics here for something that's off. And I think what I might have done is the same thing I did before. So this Ampere's law at the top here, this is covering the core and the air. And I've got that on non-solid. I need to make all of these from materials, otherwise it's not actually using the material. So I think that might be the issue here, because the inductance was really low, a lot lower than it should have been. So maybe it wasn't even using the core at all. So I'll just go through all of these. And I think these have some too. So this charge conversion, I'll do that from material also. So basically just anything that you can set to from material, that's what I'm doing. Okay, I think that's everything. So now I'll rerun it, we can check it out. Okay, here's another mistake I found. You guys probably saw this, but I gave the core the resistivity of copper. So that should be more like 1. All right, so we've got copper here. We got the core. So I'll run that again. All right, so I reran everything and it took 2 hours. So if we go back to this primary magnetizing, now we're getting 9.6 microhenries. So that's pretty good. That looks like what we wanted. The secondary is now getting 34. So there's still something wrong, but it looks like it's starting to work now that we fixed a couple of things. Yeah, I guess I should have just skipped the secondary. All right, I think I found the problem. So in this one, it's supposed to be the voltage on the primary here and 0 current on the secondary. And on this one, I've got voltage on the secondary and 1 amp on the primary here. So that's supposed to be 0. So let's check all of these. This one's primary and 0, 0, and secondary. So it's just that one. So let's rerun that. All right, looks like that fixed it. These two match now, primary and secondary. So I think that's gonna be good for now. So it looks like that took 35 minutes to run. So I guess the magnetics ones are all about that much. I think the electric ones are more in the 10-minute range. And the whole thing, I think, is 2 hours without this one. So it's 2 hours and 40 minutes or so to run all the analyses. Okay, so here's a drawing of what we got. So the primary comes in here. We have the resistance, 21 milliohms. The leakage, I put 69 nanohenries. It's pretty frequency dependent here, so I just used the 300 kilohertz option. And then the magnetizing, 9.6 microhenries. And we have the self of 4.7 picofarads and the mutual capacitance of 4 picofarads. So that's about it for now. I didn't calculate this core loss resistor. I'm gonna have to work on figuring out an easy way to do that. There's a couple of things I wanted to mention before I let you go here. I think for the core loss, what I was thinking is if we go to the physics, add physics over here, they've got, well, no, let's see, studies. They have this time-dependent study, so I think we could run a transient simulation over one switching cycle, kind of like in the ANSYS Maxwell overview I did, and maybe get the core loss from that and turn that into a resistance. That one I was having trouble with. The time-dependent analysis I tried to do wasn't really converging, and I don't think I understand that super well yet. The other thing is, if you watched the ANSYS one, we used an integrated SPICE simulator to generate the waveform, and they do sort of have that in here. If you go to the physics, you can do this electrical circuit simulator here. So we double click that. It adds this circuit. You can see that it starts off with just this ground node. And if we click on here, you can right click and add different parts. And it's similar to the COMSOL one, except there is no way to draw the schematic. So you're basically, you have this GUI for defining the spice, which is a little odd. So you have your reference designator here, and then you just tell it what the node names are for each part. So that's basically how you define it in the parameters. So you're a little bit drawing blind here unless you're really good at spice. What you can do is import a spice circuit. If I scroll up so you can see the drop down, here it has import spice netlist. So then the last thing I wanted to mention is there's this circuit extractor that's in some of the newer versions here. I'm not sure exactly what version it came out in. You go to developer and add in libraries. Then you go to this AC/DC module, and check the circuit extractor. So I did already have it checked, so it should be in here. You have to go maybe add-ins, circuit extractor. Yeah, so now we have a circuit extractor here, and you can choose these different networks that you want it to extract. Resistors, inductors, if you want all of them. So right now you can do, let's see, resistors, and it has matrix, there's nothing there. So if we do capacitors, we do have this mutual capacitance, so we could extract that and it'll make a spice file. Now if we want it to do resistors, capacitors, and inductors, we can do that and it'll let us select a matrix for each one. So we only have the capacitor one. If we want to add resistors and inductors, we need to go over here and add this magnetic fields current only. So that's under electromagnetic fields and this vector formulation. And here we go, magnetic fields currents only. This will do the inductors and resistors. So for this one, we want to add a couple of items. We want a conductor for each coil. So we'll just do a couple of these. We'll name this one primary. Select the primary, secondary, select the secondary, and we'll just leave these names terminal 1 and terminal 2. Basically just get everything from the material. So that's set up. Everything else just free space. So that should be all we need for this. So then we just add a study for that. For this one, the study we want is going to be, so for the other matrix we use this stationary source sweep. For this one we're going to use it with initialization. So that's going to give us this coil geometry initialization thing. So this one's set up correctly. It's just got the last checkbox. This one we need to uncheck everything except the last one. And you'll notice whenever you add something like this, it kind of messes up all the other ones. So you have to go through here. Now it's got multiple things. It's got the electrical circuit checked. So we need to go through. If we were going to run these again, we need to go through and uncheck the extra ones again. So we can go through, get rid of the last two. So I'm going to call this spice extraction R and L. That should be all set up. Now we can just run it. Okay, so I didn't like that. It's giving me all these resistor hanging node problems here, so I think I must have selected the wrong thing here. So we have magnetic fields on this one. Now we have magnetic fields. So I don't know why it's talking about the circuit, but I'm just going to delete, let's see. I'm just going to delete the circuit. Where is our circuit? Electrical circuit. We're not using that, or we can just disable it. Now let's try running it again. Okay, so we forgot to select the terminals. So we go back up here. We want the terminals to be input here and the input here. So we're going to just leave these as 1 amp, but I think we should also add a ground. So add a ground to each of these, and the ground will be this one and this one. So it still doesn't like that. So I don't know what just happened here, but we have overridden by the ground. So I have to clear the selection. We just want the 1 ground. So we have, there we go. I guess the ground started with everything. So we're gonna get rid of that. Just want this 1 face as the ground. Let's try that again. All right, so that's done. Now we can see it took 8 minutes and 43 seconds. Go up here to the circuit extractor, and it's got the matrix filled in here now. So we can just click extract circuit. So then that created this SPICE netlist for us. So I'm not exactly sure what that's useful for, but there is this whole article about it that I'll link in the description so you can check it out. It does look like it made some sort of a transformer model because it has this K factor, has L1 and L2, has 2 resistors. Then it's got some voltage sources. They show it in here as being sort of these networks. Here's capacitors only, making this capacitor network. Here's one with resistors and inductors. So that concludes the parasitic extraction of the transformer. I think that was pretty interesting and potentially useful, especially if you're trying to design a transformer that you can't just buy if it has custom core parts or something that make it complicated. I did not build the transformer and validate the results, so at this point we don't really know how accurate they are. I did also do some analysis with ANSYS Maxwell, so you can check out those tutorials if you haven't yet, doing a same transformer design, and got some results from that to compare and contrast. So anyway, thanks again for watching, and I'll see you next time.